Hi everyone, my name is Dorin Bassi and I work at Red Hat as a software engineer in the automotive team. So in this presentation, I'll be talking about modernizing Virtio GPU, and I'll be following a Rust-powered approach with the vhost-device-gpu. So generally, I'll be talking about the implementation of Virtio GPU that we've been working on in the Rust VMM project. So why rethink the Virtio GPU architecture? Recently, we've been seeing a broader adoption of Virtio GPU from Rust VMMs like QEMU and Crosvm to Linux and Android automotive systems, and with that comes an increase in complexity. And secondly, for us, security is a concern because many backends are written in C, and that could be unsafe. And isolation of the GPU device logic helps us to reduce the VMM's attack surface. Another reason was that we needed better modularity, especially when sharing code across different hypervisors. And given that Virtio GPU has to support newer features like the blob resource and the host visible memory, this kind of makes the C-based architecture harder to maintain in kernel. And finally, the other benefit was Rust. I'm not going to talk so much about this. I mean, a lot of people have already talked about it, Alice in the first presentation. So one of the good things is that we can leverage the Rust VMM ecosystem to simplify the development of the Virtio GPU device. So on this slide here, it shows the core of the Virtio GPU stack. And let's take a look. So first, what is the Virtio GPU? It's a paravirtualized GPU that allows the guest virtual machine to access the host GPU resources with minimal overhead. And unlike the full GPU pass-through, this method is more flexible and it works well with multiple guests. The Virtio GPU device is following the Virtio 1.2 specification, and this specification standard outlines how the 2D and 3D graphics acceleration could be virtualized efficiently. And this also enables like cross-platform compatibility between the guest and the host. For the full stack, it's consisting of the Virtio GPU driver, the PCI bus transport, and the Virtio GPU device itself, which would be on the host. And I'm talking about these components now because I'll mention them more often in like the slides. And these components kind of work together to provide the 2D and 3D acceleration. So let's take a look at the old versus the new GPU architecture. Here on the right, left, I don't know, QEMU, that's the vhost-user-gpu C variant in QEMU. It uses virglrenderer to handle the GPU rendering. And it has support for Virgil 3D mode. It has support for EDID, and it seems to be missing support for the resource blob, the context initialization, and the shared memory region. So a brief explanation of what this Virgil 3D mode does is that when that is supported, it means that the guest can actually send OpenGL-like commands through virglrenderer or like just send OpenGL commands to the backend. And for the EDID feature, when that is supported, that's like the short form for extended display identification data. It lets the guest to query the display modes from the host. So it would query information like the resolution and the refresh rate. On the right here, we replaced it with a separate vhost-device-gpu process. So this is giving us better performance and isolation while still using the same Virtio GPU guest driver inside the VM. And the vhost-device-gpu actually allows us to switch between the virglrenderer backend and the gfxstream backend. It has support for Virgil, EDID, and context initialization feature, while for the resource blob and the host visible feature there, they are not like fully upstream today, but we have patches ready and we are actively collaborating with maintainers to land these patches upstream. And for the context initialization, just to give you a brief overview, it's like a Virtio GPU feature flag that actually allows the guest to request and use separate GPU context. So instead of everyone sharing one GPU context. And this is important in a multi-VM GPU sharing setup. And this right here is our architecture for QEMU KVM as a hardware agnostic hypervisor. So what happens is first we have like a standalone virtual GPU device that's running in the host user space as you see there. And this device is like our vhost-device-gpu, and it shows up in the guest through the virtual GPU PCI bus, which kind of defines how the virtual GPU device is exposed to the guest OS. Now, the application that's running in the guest can actually make calls to the virtual GPU driver to render these graphics. And a typical example would be like, for instance, let's say an application using OpenGL or Vulkan APIs that are actually supported by the driver. It would make these calls to the virtual GPU driver, and then the virtual GPU device, on the other hand, would receive those commands in form of VetQs that you see there, and it would translate them into actions that the host GPU can understand and perform them through the corresponding host libraries and interfaces. So where are we now? Many implementations of virtual GPU are beginning to exist. QEMU itself has about 4 virtual GPU variants, and we're trying to replace the vhost-user-gpu variant with the vhost-device-gpu under the ROS-VMM project umbrella. And then there is libkern as well that we also have that has a virtual GPU device. And we also have like Crosvm having a virtual GPU device as well. And for our vhost-device-gpu, the device code was initially based off on a combination from libkern's virtual GPU and Crosvm's virtual GPU code base. And now we're leveraging the virglrenderer and the gfxstream libraries through rutabaga crates, and we're utilizing that for rendering purposes. So how do we support display in the device? The vhost-device-gpu actually supports 2 main display backends. One of them is GTK, which is the traditional method. It's like very straightforward. It just pops up a window and it shows the VM's display directly. And this is great for development and debugging. And then the second one is the dbus display, which is more advanced, and it decouples the rendering logic from QEMU itself. So this allows us to send the display somewhere else other than using QEMU. And I'll explain more in the next slide about this dbus. So what happens when we're using the dbus part? QEMU sends the display data over the system dbus to an external process, and in our case, that's SnowGlobe we're using, which handles the rendering output to the screen. And when dbus, I would say it's a bit more complex than the GTK approach, but we're focusing on improving it because it's useful for us in containerized or sandbox environments where maybe a direct access to a display server is not available. And it also gives us the flexibility that we need in cases like automotive use case or having automotive systems running multiple VMs. So let's look at the current design. In vhost-device-gpu, currently we use rutabaga GFX as an abstraction to talk to multiple backends like the virglrenderer and the gfxstream. And although virtual GPU device does not directly handle multiple backends, what happens is that it's actually interacting with rutabaga GFX through a trait interface, and that exposes a unified API to vhost-device-gpu. So from the device point of view, I would say it's modular because it doesn't need to know what backend is actually being used under the hood. And switching between backends doesn't require much change in the device logic or the VMM. You just have to like swap out the renderer. For Vulkan workloads, especially on Android, we rely on the host visible memory and the blob resource support, which are both handled by gfxstream through rutabaga. And we could also do Vulkan workloads through virglrenderer as well. So now that we understand how the renderer backend is chosen, let's take a look at the communication between QEMU and the device, how that works under the hood. So we have a virtual GPU device relying on two main protocols. One is the generic vhost-user protocol, and then the second one is the GPU-specific extension. So let me walk you through how they both work together. For the vhost-user protocol, this protocol is designed to offload the virtual device processing from QEMU to another user space process that's running on the host. And this user space process is what's like responsible for implementing the device functionality based on the specification. And as you can see here, there are like two sides for communication. We have the front end and then the back end. So the back end is the device itself, which in our case would be the vhost-device-gpu, and the front end is like the virtual machine monitor, which in our case is QEMU. I mean, we could have other backends, like we currently have in the ROSVMM project, the vhost-device-gpu in sound and other devices, which could also serve as a backend. So that's like the generic vhost-user protocol that shares it. And then we have the specific one, which is the vhost-user-gpu protocol. And we have like the backend communication socket. So for the backend communication socket, it's used for sending backend requests to the front end. And we need to use this for mapping the shared memory region. And other vhost devices use this too. Then there is the very specific GPU socket for sending messages from the backend to the front end. This socket is mainly used for things related to display handling and configuring the scan-out, or even presenting the display updates and like handling mouse cursor updates as well. Now, looking at the device design from guest commands to rendering, what happens is that the guest actually pushes those commands into vert queues, and then these commands are consumed by the control or cursor queue. And next, we have like a process queue function in the Rust backend that decodes these commands. And depending on the request type we receive, maybe we receive a set scan-out message or a resource create blob message. We have like the GPU command decoder that actually decodes the specific virtual GPU commands. And these decoded commands are being routed to the backend implementation. For the scanouts, we handle the scanouts by the device for the display. And in the end, we have the guest believing that it has control of the backend, because the backend is like safely presenting these exported buffers on the host. So currently for virglrenderer, we have support for the DMA buff scanout, which passes the file descriptor and metadata, and it's faster and like better. And for gfxstream right now, we're still using the legacy set scan-out handling in the device. So while working on this device, we encountered a couple of architectural challenges when integrating the rutabaga crates. And one of the challenges we had was the single process constraint. What that meant was that rutabaga context could only be initialized once per process, and we needed to have a workaround, which was doing a delayed initialization during the event handling. And then another issue we had was like a thread affinity problem, where renderer calls had to remain on the same thread, and this was conflicting with the multi-threaded design of the vhost-device-gpu that we have. The workaround we had for that was to use like a thread local storage to shut down the entire process when the guest shuts down, to avoid reinitialization issues. So it works differently from like the other vhost devices we have under the ROSVMM project. Another issue we faced was like the third-party dependency friction. So rutabaga relies on external Git submodules, which are not bundled with the published crate. And this kind of complicated CI and packaging issues for consumer projects like vhost-device-gpu and libkron. Like currently, libkron is, I think, vendoring a local copy of rutabaga, and this kind of highlights the need for a more crate-friendly distribution. So these challenges we had with the thread safety and tight coupling with rutabaga was what led me to rethink the architecture for some backends entirely. So rather than extending like rutabaga further, we decided to experiment with a more direct integration path using Rust. And this brings us to one of our recent developments. So one of the changes I made was building like a Rust script that wraps libvirtualrenderer directly. And this lets the vhost-device-gpu backend talk to libvirtualrenderer without having to go through rutabaga, which was originally built for Crosvm. And this gives us more control by bypassing rutabaga, because we are cutting out a lot of extra layers and the Crosvm specific logic, and this making the integration much more easier to integrate. And it also improves testability for us. And I would say, frankly, like keeping up with rutabaga felt like keeping up with the Kardashians for us, because every few months or weeks there was like a new change and new drama, and like when you think you've caught up with it, like a new API change drop, we have to like rework our device to fit the rutabaga crate. And with virglrenderer Rust crate accessing, like with us accessing it directly now, it makes the backend simpler and easier to maintain for us, especially for like projects like libkira and vhost-device-gpu, or even any other like VMM that works outside of the Crosvm ecosystem. And with this refactoring, we can introduce new backends in the future and even improve or replace the existing one. So we're currently working on using the virglrenderer Rust crate, and we're thinking there's a possibility to also have like Vulkan backend as well, so that we can like directly use Vulkan backend without having to like go through virglrenderer. And overall, I would say that this separation of concern makes the system more adaptable. So whether you're targeting Android, Linux, or like embedded automotive workloads, with the second architecture we have now, we've kind of switched the modularity from rutabaga to the vhost-device-gpu. Another recent development we had was IGT DRM IOCTLs test that I added to the IGT tools. And this includes like Virtual GPU DRM IOCTLs, like testing for that. And we tested the setup with QEMU and the vhost-device-gpu. So it helps to check that the GPU backend is actually responding correctly to the expected DRM calls. And one of the nice things about this is that you can trigger GPU commands from the guest, and some commands could be hard to reach, like the resource create blob. I mean, the Linux guest cannot just issue a resource create blob, but with this test, you can actually trigger like those kind of commands like resource create blob or set scan-out blob, and then you would see how well your backend is handling these commands, or even another virtual GPU device could use this test to see how they're handling those DRM IOCTLs. And with regards to the upstream integration, a lot of ongoing developments have been happening in the virtual GPU space, and one of them is the shared memory region support. So why is this feature important? These are the enablers for modern GPU virtualization, and without them, I would say you're stuck with the legacy 3D resource flow, and that doesn't scale very well with Vulkan or blob-based backends like the gfxstream. And I also think it's important to highlight the work that Albert Steve is doing with regards to the shared memory map and map request, because that lays the groundwork for us using blob resources in vhost-device-gpu. So with the host visible shared memory, what happens is that the front end and the back end actually agrees on a file descriptor backed region that both sides can map. And this is important for blob resources, since like the Vulkan and the modern APIs actually expect a GPU visible memory. So it's expecting that instead of like a guest, scatter, and gather list. And it allows dynamic mapping and unmapping operations. So backends like the vhost-device-gpu can actually request memory only when needed. And this would help us to save like CPU overhead. And I would say in summary, it's like an efficient resource sharing solution for us. And although I talked about the shared memory region support, which is still a work in progress, but our current device uses the resource create 3D today, which is what some other virtual GPU device uses. This resource create 3D actually lets the guest to create a geo-like resource, say textures or buffers, and then it would make a host side call to allocate the gel or Vulkan resources. But when it's doing this initially, it does it without any backing buffer attached. And then later on through the attach backing command, which is like a virtual GPU command, the memory would be attached. And unfortunately, this is not like a very efficient way to handle resources because the memory is not like inherently GPU visible. So it has to be mapped or copied, and it's resulting in like extra CPU work for us. And this led us to the blob path. So why is the blob path important? With the blob resources, following these patches that Matei worked on for inclusion in QEMU and the vhost-device-gpu, what happens is that the memory is like created at the same time as the resource. And with that, it supports the zero copy, which means that the data does not need to be copied between the guest and the host GPU memory like we're doing with the resource create 3D in the previous slide. Instead, both the guest and the host can actually access the same memory region. And this is why the zero copy blobs are faster and more efficient, given that the vhost GPU can actually render directly into the host visible memory that's being shared with the guest. Another feature that we've been looking at supporting is the resource assign UUID feature for the vhost-device-gpu. So a brief explanation of why this feature is needed and what it does is that this assign UUID actually lets the guest to assign a unique ID to a GPU resource like a blob. And then the UUID makes the GPU resource discoverable and shareable across VMMs or even across other virtual devices. And this is also important for the zero copy sharing of GPU buffers. But this would only make sense for us with the resource blob support I talked about in the previous slide, because with the older virtual GPU path, what happens is that with that resource create 3D, or maybe you're using resource create 2D, what happens is that the resource is living in the guest RAM, and they can be exported as DMA buffs. So the assign UUID is not very useful with that. And for the assign UUID, we need like a DMA buff file descriptor, which is what the virtual DMA buff code here and the resource assign UUID command actually rely on. And how do we get that descriptor now? So you would see it in the next slide. Let's walk through the shared object flow. When a guest application needs to create a shared resource, what happens is that it issues a standard resource create blob command. And this command will be received by the virtual GPU front end that's in QEMU. And that acts like a simple proxy that forwards the request to the daemon. So now our vhost-device-gpu daemon is what's responsible for creating the resource. And it would create that DMA buff file descriptor, which is the actual shared object, and it would store it internally. Next, the guest would issue like a resource assign UUID. Now, don't forget the DMA buff file descriptor that was created by resource blob, because QEMU would tie that UUID to the blob file descriptor, and it would do that in the virtual DMA buff table. So with that, you can see we have like a UUID and file descriptor mapping in the DMA buff table. So now any other virtual device like virtual video or even another VMM can actually look up that UUID through vhost user, and it will get back the file descriptor. And then with that, we can pass the file descriptor across like other devices. But to have this usable, we need to support the shared object message. So in order to support this shared object message, I already added partial support for this in the Rust VMM vhost repo through some of my patches included last year, which kind of helped to close the loop in the zero copy pipeline. And with this now I would say the UUIDs are no longer just identifiers, but they are actual shareable handles. So for the automotive use case, Red Hat's primary goal in the automotive sector, I would say, is to enable Android and other automotive operating systems to run concurrently on rivals using like a shared virtualization layer. So by leveraging the virtual GPU, these guest VMs can actually share the host GPU without needing hardware-specific drivers. And yeah, another goal for us was to ensure that Virtual GPU was compatible with the Android reference platform, which kind of specify features that are needed for Android automotive systems. And this kind of ensures that the Android automotive OS can actually run seamlessly as a guest VM. Another objective for us was like allowing multiple automotive OS to coexist by sharing the GPU. And this kind of helps to keep the guest OS independent of the underlying GPU hardware. And it kind of reduces the need for having like separate GPUs per VM. And it leads to cost savings for us. And finally, I would say this approach introduces like minimal performance overhead for us. And with the power virtualized access, we could still deliver a safe and offer multi-domain rendering for applications like infotainment or instrument clusters and navigation systems. So our main focus for gfxstream was Android support, which kind of seems to be the preferred virtualization solution. Like gfxstream is the preferred virtualization solution for Android. And actually, Android supports virglrenderer, but doesn't support like Venus, which is like the Vulkan implementation. And this is not ideal because we want to be able to actually use the modern Vulkan APIs. We're also using gfxstream for running the Linux guest as well, but we're doing that without 3D acceleration. And there is also the possibility that like we could use gfxstream for Linux guest 3D acceleration, because last year gfxstream got merged into Mesa. And then for virglrenderer, I would say that it's more suitable for virtualized graphics in like Linux-based automotive environments, especially outside of the Android ecosystem. So while Android typically uses gfxstream, like many non-Android domains like instrument clusters still use Linux VMs. And for this, I would say virglrenderer is like a simpler and stable path. And given that it has like strong OpenGL support, which is properly integrated with some toolkits, with the Venus guest driver, it could also support Vulkan. And I'm saying you can support Vulkan because we're assuming that the GPU backend is like properly set up to handle the required feature. So I took some performance matrix, and for the first performance matrix we have here was some measurements using GL Mark 2 on a Linux guest. I measured it against, I measured our vhost-device-gpu against the previous vhost-user-gpu C version. And for the on-screen performance here, you can see like the performance is like close to each other. And then when I ran GL Mark off screen, the vhost-device-gpu was outperforming the vhost-user C version. And we also ran some benchmarks running like 3D Mark on like an Android image, which is a phone image, because you can run like 3D Mark on an Android automotive like operating system image. So I started asking, can DMA buff scan-out help? So DMA buff scan-out support was like the recent support we added for virglrenderer in the vhost-device-gpu, and I also took a matrix for that on Linux by running GL Mark, and the on-screen performance was really great, and I would say the off-screen performance also did well, like it was comparing with the previous version we had for the vhost-device-gpu, which is the green bar you see there. So to run Vulkan apps inside a virtual machine, we actually rely on virglrenderer combined with Venus Vulkan guest driver. But just enabling Venus is not enough, because the backend has to support the resource blob, which is important for efficient Vulkan buffer and image handling. And you can confirm that with like doing a dmessage grep virgl. And if you see resource blob, it means that like resource blob is supported. And after we did like a setup, we validated it using Vulkan, that's vkcube, we ran that inside the guest. So that's not like a true Vulkan pass-through, but it's actually a fully virtualized Vulkan environment, because we are handling it using the path of Venus to virtual GPU to virglrenderer backend. So to verify that Vulkan rendering is actually working inside the virtual machine, I use vkmark here, which is like a simple benchmark tool to measure the Vulkan performance. So here the system is running with Venus, and the Vulkan driver is sitting on top of virtual GPU with the virglrenderer backend underneath. And we had a result of vkmark score of 448, and that confirms that we're actually getting GPU-backed rendering in the guest. So this is not like a software fallback like LLVM pipe, but it's actually proper like support that is routed through Venus. And we often think of Vulkan in terms of rendering, but actually it's a low-level compute API as well. So this lets us do more than just draw pixels. We could actually do AI inference on it too. And not just vhost-device-gpu, but also libkeyron exposes a virtual GPU device. There is this article that Kevin Puget wrote on how we improved AI inference on Mac OS Podman containers using libkeyron. Like, it would also be nice to look at that and see how you could run like AI workloads on libkeyron. And in this setup here, the guest VM actually uses virtual GPU with Venus to expose Vulkan. And then from there, we install Llama, which lets us to run models like Llama 2 in a container using the Vulkan backend. So in this video that I recorded, we can confirm that inference is actually running on Vulkan by inspecting the logs and verifying the Vulkan virtual SO file was loaded in the guest through Venus. And I did a simple query, and this response came from tiny Llama that's running inside the guest, and it's accelerated using Vulkan buffers. So here there is no OpenGL fallback or like CPU-based model runtime. And this is a proof for us that by combining virtual GPU with Venus and then having a Llama in the guest, we can actually run a real-time LLM inference without PCI pass-through. And this is done like inside the virtualized graphics stack, para-virtualized. And some updates on the virtual GPU we have. If you want to try it, we have it in the RusVMM repository. And we also have it published as well as a crate. We have it packaged as a Fedora package if you have like a Fedora distro and you want to check it out. And then we have like the virglrenderer script available in case maybe you're working on some virtual GPU related feature. You could also use the crate. And we also have like some new features coming in, like the DMA buff support for virglrenderer. And for the future work, last year I talked about this at KVM Forum, like some status updates now is that we have like improved kernel performance and we have virglrenderer script. And now like the new thing that we're looking at is maybe a web GPU backend, because someone opened up a discussion on the RusVMM vhost device about inclusion of a web GPU backend. So maybe if you're interested in like supporting or contributing to that, you could look at it under the RusVMM vhost device GPU. And yeah, that's it. Thank you. Any questions?
Great talk, by the way. Thanks for presenting. Actually, it's a dumb question, but the tests that you run, I mean, those graphs that you've shown, I'm not from the GPU area, so is like better score means it's, I mean, higher score means it's better on those tests? Okay,
yes.
Thanks.
Thank you for the presentation. I was wondering, right now with Vulkan acceleration and the new pass-through developed, how far are we from PCI pass-through in terms of performances?
Sorry, can you repeat yourself again?
Sorry. Right now, with the Venus plus Vulkan acceleration through VHL, how far are we from pure PCI pass-through acceleration for rendering? Did you run this kind of tests?
I'm not sure I get your question correctly, but why, if you're asking why Vulkan, we're currently supporting Vulkan in the guest, but we don't have it like in the backend yet. And I mean, in the future, we're looking at having a Vulkan backend that can handle those commands, because right now we're like doing virglrenderer backend in the host, and we're like doing a Vulkan in the guest. So it's virglrenderer that's handling those commands. So we're looking to support Vulkan backend in the future.
I do. What I wanted to know is just like with Virgil backend, what performances do we get right now compared to PCI pass-through?
Oh, I didn't take those metrics. I didn't take those measurements.
Okay. Thank you. Anyone else?
Yeah, good presentation, by the way. Just one simple question. You indicated that the VirtIO GPU, the new one, was supported into a separate process. Does that mean that it's a separate process per QEMU guest, or it's a one process for the whole platform, the whole set of virtualized guests?
Mm-hmm. Yeah, you can actually set up actually separate processes, and you like attach different sockets, and then the QEMU guest, you like specify the socket of that process that you specified on the backend. So you can have like 2 or 3 separate processes run and like have different VMs access those processes through the socket.
I don't know anything about automotive systems. Do they always use VMs? Or?
So we are looking at supporting VMs, because sometimes in like the safety point of view, we have like ACOD, like very critical components, and then we have like less critical applications. So we want to have a way to run those less critical applications using VMs, which I think it's a safe way to handle things. So that's why we're going through this approach.
Okay.
How many VMs can be run under in this use case? Can you have as many VMs as you want sharing a single GPU with virglrenderer?
Yes, exactly.
Thanks. Thank you.
Okay, thank you.